This video will be going over section 4.1, which is an introduction to exponential functions. In this section, we're pretty much going to define an exponential function, what it is right away. I'll talk about the parts of it, and then we'll do a couple things with exponential functions. One is going to look pretty similar to figure out an equation of a line based on what we're given, but it'll be different because we're talking about an exponential function. And then we'll see a couple word problems, when exponential functions would pop up, what they're used for. All right, so the first thing is the definition of an exponential function. What we do, our definition here, we let a, b, and k be any real numbers with the condition that b is positive, b is greater than 0, and b does not equal 1. Then an exponential function is written as f of x equals a times b to the x power plus k. All right, so this is a general exponential function. When we deal with graphs in the next section, it ultimately will be boiling down to figuring out a, b, and k as well. There's not other things we'd have to worry about. Now, the important thing here, b has a special name. You'll notice our variable x is in the exponent. That's why it's called an exponential function. B is given the letter b because it's called the base. That one's not randomly chosen. And the important thing about the base is it must be positive and it cannot equal 1. A can be anything at all, k can be anything at all, as long as they're real numbers. We don't want any i's popping up here. And another thing I want to add, we'll see this when we do the problems, is the letter a is not being raised to the x power. So when you have a times b to the x, if it's like 3 times 4 to the x, that is it. It won't be 12 to the x. But once again, we'll see that in a couple problems. Most of the examples we do will be with k equals 0. You'll be told that in some way in the problem if k equals 0. But what the k is going to do is more relevant to our graphs. It shifts the graphs up and down. All right, we'll see more of that next section. All right, so really what we're doing here is just based on some problems. These first two are more general. We're going to be given 2 points. We want to figure out the a and b for the equation f of x equals a times b to the x. And then the second part of this, the next two problems below, will be word problems. It gives you kind of a feel of what exponential functions are used for. Right. So like I said, we'll go ahead and work these two. For the following, assume f of x equals a times b to the x. It is telling you that this plus k is 0. We don't have to worry about it. What we want to do is find the values of a and b. And right here, I have outlined how you'll do these problems. For problems like this, you start by plugging in the given points for x and y. So we have x is 0 when y is 7 is one of our points, and x is 3 when y is 448 is another one of our points. What we do is we plug these into our equation that we're given here, and it'll allow us in some way to solve for a and b. Okay, so what I'm going to do, I'm going to plug in each one. Now you can plug them in right next to each other. It just depends. When you plug them in, maybe you can figure some stuff out right away, maybe you cannot. Right, but we have y equals a times b to the x. Y is 7 equals a times b to the 0 power. I'm just going to plug in each one and then worry about simplifying and doing things with them after. With the other one, we want to plug in y is 448. Y equals a times b to the x. X is 3. It's a little messy. Let me redo that 3. So we're going to be able to solve for both a and b in this problem from these two equations. Now this one actually works out pretty nicely when you have x equals 0 because of what happens here. Anything raised to the 0 power, even though we don't know what b is, anything raised to the 0 power, I think I mentioned this before in a previous video, basically before calculus, anything raised to the 0 power is 1. You'll see some examples in that class where it's not quite true, but anything raised to the 0 power is 1 in this class. We're not going to see any of those different type of examples. Right? It doesn't matter what b is. B could be 2, it could be 1/2, it can be any positive number that's not 1 according to our rule. And we're going to go ahead and just plug that in. We got 7 equals a times 1. A times 1 is just a, and actually this told us right away what a is. A equals 7. And that's part of what we want to solve. We want to find the values for a and b, and we got a. Now that we were lucky enough to find a right away, we can plug it into our other equation and solve for b. So if we go ahead and plug in a as 7, we got 448 equals 7 times b cubed. Now remember what I talked about at the beginning. The a is by itself. Well, it's being multiplied, but it's by itself. B is raised to the power. So it's just 7 times b cubed. And we want to solve for b. That's what we're trying to do. We already found a, which is nice. We can solve for b. Anytime you want to solve for a variable or a letter and you only have one term, you get that term by itself. We can get rid of the 7 by dividing each side by 7. And then we get b cubed equals 448 divided by 7. Just super make sure that I don't mess this up. I'll do it in the calculator. We get 64. And now to go from b cubed to b, you want to knock that power off. I'll remind you of something I did in the last chapter. I'm going to keep doing this. If you want to get rid of a power, you can raise each side to the reciprocal of that power, or 1 over that power. If we raise each side to the 1/3 power, then the 3 and the 1/3 knock each other off here. That's the point. And we get b equals 64 to the 1/3. Once again, you can type this in your calculator. If you remember, the 1/3 power means the cube root. You might know the cube root of 64 as well, but it is exactly 4. So we've got a equals 7 and b equals 4. Now, as far as this question goes, that's what it asked for. It asked for a and b. I think it's worth just writing what the function would be, plugging it in. That's what we're going to have to do in the next part anyway with the word problems. If you plug this in, we get f of x equals a times b to the x power. We have 7 times 4 to the x power. This is it. This is simplified. You cannot combine the 7 and the 4 because 7's raised to the 1 power, 4 is raised to the x power. They are raised to different powers. This is simplified. You cannot combine the 7 and the 4. So, especially the reason this problem worked out so quickly was because we were given a point when x is 0, and that let us solve for a very quickly. One thing I do want to point out here, because this is far more applicable when you do word problems, which we're going to see some in this section, and it is the entirety of the last section of this chapter. When you're dealing with exponential functions like this, a is always the initial value. Right, so if this represented some sort of population, our A, our 7 would be the initial population. It's when x is 0, if your variable is t, if you're talking about time, t equals 0, whichever one. Right, now this next one down here, we do not have the same sort of thing. Oh, neither of these have x equals 0 in them, but we still have to start by plugging them in. There's really nowhere else you can go from here. I'll actually leave this in view for a second. We want to plug in x is -1 and y is 1,000 into our f of x equals a times b to the x, and x is 1 and y is 4. It's really not going to matter which one you plug in first because you're going to have to work with both of these together. So we got y equals 1,000 and that equals a times b to the x power, which is -1. And here we got y, which is 4, equals a times b to the x power, x is 1. Once again, I'm just getting that from the formula they told us it follows. So what we have here is very, very different. We have to figure out both a and b, but neither went away by themselves. Now, there are a number of ways to start solving this, but I'm going to give you one way that works every single time. Now, one thing you can do whenever you have two equations is you're always allowed to add the equations together. You can subtract the equations together, you can multiply the equations together, and you can divide the equations. And the way these are set up, if you divide the two equations, what's going to happen is the a's will cancel out. And that'll let us solve for b. And I'll show you what I mean by divide the equations because you may have never done this before. But it'll look very literally like we're dividing the two. So what I'm talking about is our first equation on the left here is 1,000 equals a times b to the -1. And if we divide the 1,000 by the 4 on this side, then we can divide the a times b to the -1 over a times b. You can leave the 1 power there or get rid of it. Because of exponent rules in the next part, it might be nice just to keep it there. But the reason this works is you're pretty much doing the same thing to each side of your equation. It's like dividing this side by 4 and this side. It looks different, but we're told it's the same thing. We are dividing each side by the same thing. You are allowed to do this. I'm not making math up. Right, but the whole reason I like to do it this way is it's going to work every time because the way your equation is, they both always have an a here, and a divided by a, even though we don't know what a is, it's going to cancel out. And now simplify the rest. The left side, 1,000 over 4, works out to be 250. And the right side, we have b to the -1 over b to the 1. Now you can use exponent rules here to get b to one single power. Remember, when you're dividing, you can do the top minus the bottom. -1 minus 1 is -2 is the exponent. Right. Now to go and get b from b to the -2, this is why I like to do it the way I showed you before. You don't have to do it like this, but I just like to do it like this. We want to make each side have the one exponent. If I raise each side to the reciprocal of -2, which is -1/2, then the two exponents over here cancel out. The negatives cancel out and the 2's cancel out. And we've got b equals 250 to the negative 1/2. Now you can do a little bit to simplify this. It's not going to simplify much. What you don't want to do is write this as a decimal. Very few homework problems in this class allow decimals. It's pretty much just the word problems. But if you don't like negative exponents, you can always make an exponent positive by flipping the inside. So if we make the inside 250, 1 over 250, it switches the sign on the exponent. So this might be some review of exponent rules you haven't seen in a while. Right, most people don't like looking at negative exponents. They prefer positive exponents. Excuse me. And if you want to go even one step further, 1/2 as an exponent is the same thing as the square root. And we talked a little bit about that in the previous chapter as well, when we were dealing with polynomials and why you can't have radicals for polynomials. I didn't mean to write that. 1/2 exponent is the same as the square root. Now, since the square root of 250 doesn't simplify much, it's not a perfect square. You would be able to simplify it a little bit, but it's not very useful. So I'm just not going to do anything more here. If you leave b as the square root of 1 over 250, that's okay. In fact, I don't even have a problem with leaving b as this, 250 to the negative 1/2. What I do have a problem with is using decimals when you're not supposed to. Okay, so if the directions would be very clear on a test type of situation, unless if you're allowed to use decimals, don't. So just make sure you use one of these 3 forms. You can even simplify this a little more if you'd like, but that's where we're at is fine. All right, so once we figured out b, we do the same thing as last time. Last time we found a first because we were lucky. This time we found b first. It doesn't really matter, that happened. What we do is we take either one of our equations. I'm going to use this one on the left because the numbers are better. 4 equals a times b, and plug in what we got for b, which we got square root of 1 over 250. I'm going to plug that in to get a. So we got 4 equals a, which is our unknown, times b, which is the square root of 1 over 250. Now to get a by itself, you would divide by the square root of 1 over 250, or even easier, multiply each side by the square root of 250. Now, just to show you the very brief step of why this works, these are going to cancel out because when you multiply square roots, we can multiply their insides. And then if we simplify this, the 250s cancel out and we're left with the square root of 1, which is just 1. And the right side, we got 4 times the square root of 250. Once again, it's fine if you do not simplify this. When square roots don't simplify perfectly, I'm not overly concerned about them. If you want to simplify this, you can realize that 250 is 25 times 10. And square root of 25 is 5. Write it on the side here. Square root of 10 does not simplify, so that's stuck inside. Right, the 25 comes out of the square root as 5. The 10 is stuck inside the square root. And we get 20. 4 times 5 is 20 times the square root of 10 is a. All right, this one, the numbers are pretty messy. Sometimes they're messy the way they generate. Sometimes they are still nice whole numbers. It just depends. But very common throughout this chapter because of how exponential functions work to get radicals and exponents with fractions in them for final answers. All right, but as for a and b, and that's it. If you want to write this as the exponential function, we can do that. F of x equals a, 20 times the square root of 10, times b, the square root of 1 over 250 to the x power. But once again, I will remind you, these do not interact in any way. You don't want to try to simplify the square root and cancel out with something over here, because this is raised to the x power and this is not. So there's nothing more to do there. All right, but as far as these problems go, some of them you're given 0, much easier. Some of them you're not given 0, and you need to figure out a way to solve them. Dividing always works. So the last main topic in this section is just dealing with word problems, and I like to do a couple of these. They're not super heavy-handed. The reason I like to do a couple of these is it just gives you an idea of what exponential functions are used for. I have right here, exponential functions occur naturally when something grows or decays at a constant rate, but that rate is a certain percentage. So I can kind of just say an example right now. Some of you probably know what the half-life of something is, or the general idea. If the half-life, let's say the half-life of carbon is 100 years, which is probably a huge lie, but for the sake of argument, what that means is after 100 years, it will decay 50%, and then after another 100 years, it will decay 50%. But if you think about how much it's losing, if it starts at 500 milligrams, in 100 years, it'll go to 250, and 100 more years, it'll go to 125, and 100 more years, it'll go to half of 125. And so it decays at a percentage, and that percentage is based on the number there is. Right. But half-life is a big topic in the last section of this chapter, which we'll get to in more detail. This first one we have here, we are told a population numbers 15,000 organisms initially and increases by 8.9% each year. Suppose capital P represents population and T is the number of years of growth. Sometimes you are told this model, sometimes you are not. An exponential model for the population can be written in the form P equals A times B to the T power. It's pretty much giving us the same question as before. As far as we have the same formula, the question is what is A and B? All right, so one thing I want to remind you of here, I'll show that it still works out with the word problems, is that A right here is representing the initial amount. It can be organisms like this. It can be really any kind of amount. It can be money. If you deposit money into a bank account, it'll grow exponentially, usually, hopefully. And our initial amount here is 15,000 organisms. Now, just to show you why this is true, once again, what initial means is we would plug in T equals 0. And they're telling you the population initially is 15,000. This is almost like giving us the XY pair from before. If we plug that in, to our formula. P is 15,000. And this equals A times B to the T power, which is 0. And like before, the reason this always works out, B to the 0 equals 1. So it goes away, and we get A equals 15,000. I think it's something that's definitely worth understanding, but it's also a very, very useful shortcut to realize that A in this type of formula represents the initial amount. It's like how when you have y equals mx plus b and you know b is the y-intercept. If you're given the y-intercept in a problem, you just plug it in. You don't try to necessarily figure it out. All right, so we got A. The other question, B, is answered very differently in this problem as opposed to the previous section. All right, so B is the base of the exponent, which has to do with the way it's increasing. All right, B, when you're given a percentage like this and you want to figure out B, if our population is not changing, we kind of think about 100%. B would be 100% because it would be 1. So if the population didn't change, B would be 100%, and we would switch that to a decimal. But we are told it's changing, and we are told it's increasing by 8.9% each year. So what that is telling us is that we're increasing, so we add, and it's increasing by 8.9% each year. So if the population didn't change, we would stop at 100%. Since it's changing and increasing, we add. If it was decreasing, we would subtract. And we got 8.9%. Now, since both these are percentages, just add them together. 100 plus 8.9 is 108.9%. The one thing you want to be very, very careful about in math, we don't put percentages in our formulas. We got to switch it to a decimal by moving the decimal over twice. Unless you are told to use percentages in a problem, you will not actually ever write a percentage. And so just a reminder, I know this might be something that you haven't done in a very long time, but to go from a percentage to a decimal, we move the decimal to the left 2 spots. And we get 1.089 for a B. Now this one, like the previous 2 problems, only asked for A and B. It didn't ask you to actually write the equation, but I think for the sake of just practicing, we should do that. P equals A, 15,000 times B, 1.089 to the T power. But once again, you do not multiply these numbers together. They do not interact. 1.089 is raised to the T power. 15,000 is raised to the invisible 1 power. All right, so the next one, it doesn't give you the formula. It's supposed to be implied you're using this formula. So I'm just going to go ahead and write the formula down. Whenever you're dealing with a percentage change, which we can just see right here, that we see the percentage, you are having exponential change. Right, so one way to characterize exponential functions is they change by a percentage of their amount. Right, but this one, it's going to ask us a little more from us, not too terribly much. It says a vehicle is purchased for $27,500 and depreciates at a constant rate of 9%. And depreciate just means decreases. The value goes down, which for cars makes sense. And it's probably significantly more than 9%. I think if you tried to sell a 5-year-old car back that cost $27,500 to a dealership, they would not give you what this problem would claim to give you. The question is to determine the approximate value. So this is where you can use decimals. Approximate means use decimals. And you're told how far to round. And we want to round to the nearest whole dollar. All right, so the main thing of what we want to do here is we want to take all these numbers that we were given and know how to plug one in. All right, we're trying to figure out P, how much it's worth. And in our problem, we have to be able to figure out what to plug in for A, B, and T. Right, this one's not asking for the function, it's asking for the actual number that we're going to get. And if you think about initial value, that's going to be how much you paid for it. It's initially valued at $27,500. And that is what A represents. Now B has to do with the percentage is changing and how it changes like last time. We start with 100%. Depreciates means it's decreasing. So we subtract. And it's depreciating at 9%. So make sure you go ahead, simplify this out, and switch it to a decimal. 100 minus 9 is 91%. And 91%, if we move the decimal place twice, it's at the end of the 91, we get 0.91. We'll use for B. And then the last one, T. T is the amount of years, which is 12. So if we plug in A, 27,500, we plug in B, 0.91, and we plug in T is 12, we will get our answer. We got P equals 27,500 times 0.91. You can put parentheses or do the multiplication sign, it doesn't matter, to the 12 power. I'll probably go back and forth all the time. Right, but you want to type this in your calculator because we are rounding. I like to type in the whole thing, and the TI-84 can do that pretty easily. If you can't type in the whole thing at once, you should type this part in first, the part with the exponent first, because that's our order of operations. Exponents come before multiplications. Right. So we got 27,500 times 0.91 raised to the 12th power. Your calculator is going to know order of operations. It's going to know what to do here. And we get 88.68 rounded to the nearest whole number dollars. Okay, so apparently after 12 years, this vehicle is worth $8,868. And anyone that has probably tried to sell a car that's even only 5 years old probably wouldn't get offered anywhere near that. But that's the problem. Okay. So that's just a little preview of what we're going to be using exponential functions for at the end. It's all about how they change. They change at a constant rate of a percentage. The next section will be on graphs of exponential functions, so we can see what a graph of one looks like then.